Hello everyone and very welcome to this video. My name is Dr. Lucas du Plessis. I'm a senior lecturer in the Department of Mechanical and Aeronautical Engineering at the University of Pretoria, and this tutorial is specifically created for my MOW, that's Manufacturing and Design module, the second year Mechanical and Industrial Engineering students, but of course anyone else who is interested in FreeCAD and creating detailed mechanical drawings will also find value in this video, or that's at least what I hope. So let's jump right in. This is the memorandum video for practicum 4, which the mow217 students completed, and in this practicum it follows on practicum 3. There's a separate video for the memorandum of practicum 3. So in this video, we will create or we will dimension the views of the base profile stage 2 drawing, as well as the side plate. Okay, the side plate that's highlighted here. So just to show you what it looks like, so the only difference between the stage 1 base profile and the stage 2 base profile is these holes, these two holes that are machined into the base profile. And I'll show you exactly how we're going to dimension it. If I can just jump back to this view, the reason for those holes is to accommodate dowel pins that run all the way through the base profile. And the reason for the dowel pins is to align the two side plates when you assemble them on both sides of the Shigley-Hauler gearbox. Alright, so the mechanism that we will use, or the method that we will use to do the alignment, is with a high precision hole on the one side of the side plate and a slot on the other side of the side plate. Okay, so both, so you can obviously now understand and appreciate that the fit between the dowel and the hole, and the fit between the dowel and the slot in terms of the width of the slot, those fits are nice or very accurate sliding fits. Okay, we don't want too much of play or clearance there. Alright, so that's in a nutshell. I think let me just show you the, yes, so this is the detailed mechanical drawing of the base profile stage B, dimensionless. So I only show the views, and this is now it depends how you want to define it, but we've got the two views. It's either the front or top view, sorry, and this will be the front view, top view, front view, and then we've got a section AA, and that section is now scaled a little bit bigger, and there you can clearly see in this section that the hole goes all the way through, and so these views are sufficient for the dimensioning of the stage 2 base profile. Right, then for the side plate right, I also have a number of views. Let me maybe do this quickly. Yes, that will work. So I've got the front view over here with a number of sections. I also indicated, if I can zoom in a little bit, so I've also indicated that these holes are aligned vertically, so they are at the same height, and I've got a section view through this hole with its tapped holes in detail 3. So this is section CC I'm referring to. So section CC shows the detail of this interface over here. That's a bearing interface. And we'll say more about that in one of the future practicums. Section BB, if I can just, section BB runs through the dowel hole and these fastener holes, these counter bore fastener holes. So, and I've specifically highlighting detail 2, which is this detail over here. So we will very successfully be able to dimension this counter bore hole here. And detail 3 will enable us to dimension all the necessary features related to that bearing interface that I just spoke about. Okay, and then also on the front view, we've got section FF, which is shown here on the right hand side. Okay, and this now, the idea here of section FF is for us to make a dimension of the width of the slot, the dowel slot. Over here at the bottom, I'm showing detail 1. Okay, and detail 1 is also, it actually, the parent view is the front view. This is detail 1. And then also in detail 1, I'm showing section AA, which will enable us and allow us to dimension the horizontal distances between the counter bore holes, as well as the distance from the dowel hole to the dowel slot. Okay, and then lastly, we also have an isometric view just for clarification purposes, and we'll speak about the notes. This was part of practicum 4. Students were supposed to add notes for this side plate right as well. Okay, but we'll talk about the way that the side plate right is manufactured. I did mention it in the information video, but we'll talk about that also when we dimension the side plate right. So what you see on the screen at the moment is the OCR form that the students were issued with. And specifically, this is the front view of the base profile stage 2, where you can where the section AA is indicated. The second page is indeed then the view of section AA, and then we've got also the top view. All right. So I will speak about the side plate right in a minute, but all the views that we showed on the yes, let me just add that. So for this practicum, we will dimension all the features which for which there are views, detailed views. So these two features where my hand is hovering now, this hole, this bearing interface over here and this bearing interface over here, is not dimensioned as part of this practicum. For manufacturing purposes, if you wanted to manufacture this side plate right, you will obviously detail all the features. Each and every feature needs to be dimensioned. But since these two bearing interfaces are very similar to this bearing interface over here, from an exercise point of view, it doesn't make sense for students to repeat exactly the same thing 3 times or 2 times. All right, so okay, let's jump right in. The base profile stage 2, we need to plan where we're going to put which dimensions on the OCR form. So my strategy will be to use this top view and front view to indicate reference dimensions, as well as the datums that we will use to add the position tolerancing for the 2 dowel holes that get machined in the base profile. Note, ladies and gentlemen, the length of this base profile stage B will also be a reference dimension. It will definitely not have tolerancing, because the length is not machined as part of the stage 2 operation. The only features that get machined in the stage 2 operation are these 2 dowel holes. These 4 holes, these 4 clearance holes, are also not machined as part of stage 2 operation. they were machined as part of the stage 1 operation, and we will not even put any reference dimensions for those 4 clearance holes. Okay, so if you can't remember the length, you can obviously use a FreeCAD's manipulator workbench to take a few measurements. Let's do that quickly. So if I click on the caliper, I will leave the default snap to end point, middle point, or center point. Okay, I will zoom in and make sure that I select this face and this face over here. Okay, and there's 350. Alternatively, you can also select this length icon and click any one of the edges. It will also give you 350. So that's the length. In terms of the width, let's just quickly have a look. So if you click on that face and that face, that should give us a 90. That's right, DS and DX both are 90 millimeters, and the height should be 30. So if we click on this face and this face over here, that should give us a 30 millimeters, which is correct. Okay, so let's quickly do that. So on the top view, you can see the 350 millimeter, 90 millimeter reference dimensions, and I've indicated datums B and C. You could, and here you can see the 2 different ways. You can put the datum leader line touching the actual surface represented by this horizontal line, or you can put the datum leader line on the extension line of your dimension. Right, and if we look at the front view, here you can see the reference 30 millimeter dimension, and once again I've broken the leader line of the dimension line where it intersects with the cross, or with the arrow, and I've now indicated datum A touching the bottom horizontal line, so it indicates that datum A is that bottom surface. Alternatively, and you will see later on why I choose to do this. The alternative is to select the symmetry plane between the top and bottom surfaces as datum A. That's the alternative. And if you wanted to do that, you have to put the datum leader line in line with the dimension line. Okay, so both are correct. I just think, and you will see why in a minute, I think this will lead to a more elegant way of specifying the location and orientation of these 2 dowel holes. So the 2 dowel holes are then the remaining features that need to be dimensioned. We will dimension the theoretically exact distance between this right hand side hole and datum C, because that line represents datum C that we indicated on that view over there. And then we'll measure, or we'll indicate the theoretically exact dimension, horizontal dimension between the 2 lines. And then on this view, on the front view, we will indicate the distance from datum A to both of those dowel holes. And then what we'll also do on section AA, this is where we will indicate the diameter, the size of the hole, the dowel holes, the tolerance, plus the positional tolerance, as well as the orientation tolerance. So okay, so let's quickly take a few measurements. We can select the previous measurements in the model tree and delete them. Right, so what we want is we want the distance from the dowel hole to this face, and now we must once again have a look. It is in line with the blue axis. The blue axis is the Z axis, and that's 15 millimeters. Okay, and if we select that dowel and we go to the next one, that's 320 millimeters, also in the Z direction, so that's okay. And just for verification purposes, we can select that dowel hole, and this surface over here, Z is once again 15, which corresponds to the opposite size. Okay, and then we want to know the distance from the hole to this face, and this is now green, which is the y-axis. So if we just go down to where that dimension is, y is 15 millimeters. That's as expected, because we know that the height or thickness of this aluminium profile is 30 millimeters. So the hole is exactly in the middle, so that's 15. To verify that, just for completeness sake, we can once again click on the hole and click this top surface, and then that Y will also be 15 millimeters. Alright, so we've got all the dimensions. Now we can add this distance from datum A, and on the section view AA we can add that 15 millimeter, 320, as well as the diameter and tolerance of the hole. Okay, so I've indicated the theoretically exact 15 millimeter dimension from datum A to the center line of the two dowel holes, and then on section view AA I've also indicated the basic or theoretically exact dimensions, 15 millimeters from datum C to this dowel hole, and 320 millimeters between the two dowel holes. Right, so it's important, the theoretically exact dimension is always from the datum that we've specified. So if we were to have specified the datum on the top surface, we would have indicated the 15 millimeters from the top surface. Okay, I'll get back to the scenario where what happens if we select the symmetry plane as datum A. I'll get back to that scenario, but just note, in this case, datum A is the bottom surface, so we have to indicate the basic or theoretically exact dimension from the bottom. And then if I can go to the top view, here we've specified datum C as the right hand surface. So on this view we have to also specify the theoretically exact dimension from the right surface to this hole, center axis of the hole, and then the theoretically exact dimension between the two center axes of the hole. You could have also shown this theoretically exact dimension from the surface if space allows you to do so, but there's nothing wrong with what we've done here. Then the holes, I will specify the size of the holes in a minute. I first need to measure the hole size, but what I want to show you now here is the fact that we've got our tolerance box leader line in line with the dimension line. Even though the dimension is not shown, the leader line is indeed in line with the leader line of the dimension. We've got a positional tolerance, diameter 0,4 relative to A, B, C, A being our primary, B secondary, and C tertiary datums. So this 0,4 is quite a loose tolerance. The reason why we can live with that is if we look at this assembly over here, we've got a slot in the side plate right, and that slot length I think is about 3 or 4 millimeters long. So if we have a positional tolerance of diameter 0,4 for those two dowel holes, it will work perfectly. Okay, this dowel hole is obviously now placed in a certain location, and then relative, well, not relative, both those dowel holes are placed relative to the datums we've selected as with a diameter of 0,4. So that will work perfectly because the interfacing component has a slot on one end, and the size, the length of that slot is 3 or 4 millimeters. So it's 10 times bigger than the tolerance we specified, so which is more than adequate. Okay, so that's the positional tolerance. Now, the elegant part of specifying datum A as we've done it here, we can now, on top of the, or in addition to the positional tolerance, specify that the center axes of those two dowel holes have to be parallel to within a diameter. And here is a mistake, actually. That shouldn't be, that line shouldn't be there. So parallel to within a diameter of 0,1 relative to A. This is very elegant. Datum A is a big surface. So okay, the rule of thumb for selecting your primary, secondary and tertiary datums, choose the biggest possible surface for your primary datum, or the longest center axis. If it's a round feature, choose a long or very big long axis, center axis, or a big surface as your primary, the second biggest surface or the second longest axis as your secondary. And that's exactly what we've done here. If I can just find it. So datum B is this surface, this front surface indicated by this horizontal line. And datum C is the smallest surface. If I can just find that quickly. Yes, datum C is then the smallest surface. Right, so very elegant way. I will show you the alternative methodology if we were to select the symmetry plane, what I would recommend doing then. But I'll show that in a minute. Okay, so let us now dimension the diameter of the two dowel holes. And in order to do that, we go back to FreeCAD, Manipulator Workbench. We select this caliper, make sure that this caliper is selected, and we will get a radius of an arc or a circle. Zoom in, click on the diameter, the radius is 5, so in other words the diameter is 10. So these holes are to allocate or to for dowels to be inserted, and the dowel will be a precision, or is a precision ground mechanical component. So the hole will also be correspondingly accurate. Okay, and the dowel that we will be using is a 10 millimeter diameter by 120 millimeters long, and it will have an H6 isometric tolerance in terms of the diameter. So if we go to this tolerance finder spreadsheet and we type in the nominal or basic size, the shaft or the dowel in this case is an H6, and what I recommend we use for the whole diameter tolerance is a capital H7. So here you can see the maximum clearance will be 24 micron, and the minimum is 0. So that's what I recommend we do. So let's then add the diameter 10 with the tolerance of plus 15 plus 0 for the two dowel holes. So here you can see I've indicated that there are two holes with the fact that I've shown 2 times diameter 10 H7, and then in brackets I give the tolerance that we just saw on the spreadsheet, and that is plus 0.015. You don't have to add the plus, especially if there's no minus, and at the minimum the tolerance is 0. And then I've also extended the leader line of the dimension line to indicate the surface texture of 1,6. Note that the triangle of the surface texture symbol is pointing towards in the direction of where there is material. Okay, between these two leader lines there is no material because that's where the hole is drilled, but towards in the direction of the arrow, in other words, in this area over here, in this region, there is material, and that's how you decide on the orientation of the surface texture symbol. The text can either be horizontally orientated or orientated as shown. You cannot flip the text around. That will be upside down, and you can obviously not put text upside down on a detailed mechanical drawing. What you see on the screen is the alternative tolerancing scheme, where datum A is now the symmetry plane between the upper and lower surfaces. In terms of specifying the two holes, this part is exactly the same, indicating that there are two holes, diameter 10, H7, between 15 micron and 0 micron. That's the tolerance range. We also have in line, definitely in line with the dimension line, we've got the leader of the tolerance box, positional, diameter 0,4, and then we're saying primary datum A, secondary datum is now C, where previously we had the secondary datum as B. If I can quickly show you. Over here, I selected datum B as the secondary datum and datum C as the tertiary datum. Okay, where datum B is now this surface and datum C that surface. So both options are correct. I think that this scheme over here, where we've got B as the secondary datum and C as the tertiary datum, is a little bit better, purely based on the fact that datum B is a larger surface than datum C, firstly, and secondly, datum C is a machine surface. So for the guy to align relative to datum C, you can end up with ambiguity there. But in the fact that our tolerance zone is quite large, diameter, 4, I think both would be okay. It wouldn't be a problem. If your tolerance zone was a lot smaller, for example, diameter 0.05 or smaller, then I think going for B as your secondary datum would be advisable. Okay. Going back to the alternative tolerancing scheme, in this case, what I did was I specified the orientation of the holes as perpendicular relative to datum B. Datum B now being this bottom surface over here. And in all honesty, I think it would have been better to say parallel to diameter 0,1 relative to datum A. Datum A being the symmetry plane. That would have been better because once again, if you look at datum B, datum B being this surface, we are looking at that surface as datum B in this view. It's only 30 millimeters tall. So if you now say the hole, which is 90 millimeters deep, must be perpendicular to this surface that is 30 millimeters tall, it can be problematic. Whereas if you say the orientation of the hole must be parallel to datum A, then the surface of datum A is a plane that is 350 by 90 millimeters. And to remain parallel to that surface, or to measure and inspect whether the hole is indeed parallel to that datum, is, I think, more elegant than what I've done here. This isn't incorrect, and again, the tolerance zone isn't exorbitantly small, so I think it can work, but my recommendation would be to say positional, diameter 0.4, A as your primary datum, being the symmetry plane, then B as the secondary datum, C as the tertiary datum. And what I would do here is I would say parallel, diameter 0.1 relative to A. Okay, so this is just my honest reflection on what I've done here. Remember, tolerancing GD&T is a language in which you communicate what the extents of the imperfections are that you can live with. And there is more than one way of communicating that to the manufacturer. Okay, there are better ways that are easier for the manufacturer, and that's obviously what we aim to specify, because that will drive the costs down. And necessarily the ways that are easier to manufacture are always, or oftentimes, also very easy to inspect afterwards. And that's also something that we definitely want to achieve. We want to achieve, because once we receive, if we order 1,000 of these parts, we want to be able to inspect and without any ambiguity say whether a part is good or not. So if your tolerancing scheme enables repeatable measurements that are reliable and that you can trust, it's so much the better. Okay, so with that said, thank you very much. This concludes, or before I conclude, there's one more. Let's just go through the notes. Okay, and there over here there's actually a mistake. Even though the material is aluminium profile PG 30 by 98 slots, in this case the material for base profile stage 1 is actually base profile stage 1. Let me just repeat, the material for the current base profile stage 2, which is the drawing we're looking at the moment, is base profile stage 1. And then in brackets you can say aluminium profile PG 30 if you like. But it is incorrect to say just aluminium profile, because the person manufacturing base profile stage 2 will not start from a length of aluminium profile. He will start with base profile stage 1 and then machine these two dowel holes in that base profile stage 1. The rest is correct. Surface texture RA 3,2 unless otherwise specified, and for the holes we've specified RA of 1,6. And sorry, I actually see a mistake here. This 1,6 is the wrong way around. This is incorrect. It should be in this orientation, 1,6. So it's actually good that I show you that. This is incorrect. Wrongly orientated. Okay, the brakes all unspecified sharp edges to 0,3 max by 45 plus minus 5. That's fine. And the unspecified fillet radii to be R 0,4 max. That's also okay. It's safe to add these notes even if there are not any prominent fillet radii. It's safe to have this set of notes as a as a standard. The fifth note that you can add that I didn't add here is to say surface finish. In this case, there's no special surface finish needed, but if you wanted the part to be painted or coated, then you can specify it under surface finish. So that concludes the base profile stage 2 drawing. I will now carry on with the side plate. So this is the step file of the side plate right. If we look at the view, the front view if you like, the details that we are going to dimension, as I said before, obviously all the countersink holes we need to dimension, definitely the dowel slot and dowel hole, and then we'll focus on this, on the detail over here. We will not be dimensioning these details as part of this memorandum discussion, although if you were to manufacture this component, you will have to dimension all the details that you want to be machined. That goes without saying, because without dimensions it's impossible to manufacture a component. Right, so having a look at let's have a look at this dimensionless detail mechanical drawing showing the views that I'm expecting the students to dimension. So we've got the front view, we've got a section AA over here, section BB being this section over here, section CC, that section over there, and section FF. In section BB we isolate detail 2, in section CC we isolate detail 3, and section FF we will use to dimension the width of the slot, but we'll get to that detail. Detail 1, which is referenced in the front view, that's shown just below section FF, and that's done on purpose because the slot is then close by. Right. So the first step will be for us, when you start a drawing like this, is firstly, this is my recommendation, put in the overall dimensions. Okay, so we want a length and a height and a thickness. Okay, so these are the sure, you can put the height in any of these section views, but have them close by, have them together in one view. In one view the guy can see what the length and what the height is, and then in one of these section views, I will use this section view, I will put the thickness of this polycarbonate plate. To dimension the length, we go to the manipulator workbench, inside FreeCAD, click on the caliper, click on that caliper. We want a length, so we can select that edge, and it's 350. We can select that edge over there, that's 214, and then the thickness is a bit, if we select the the thickness, you will see 12.5, but you can't put 12.5 as the thickness of this plate, because it is manufactured from a standard 12mm thick polycarbonate. Now the reason why I made the step file as 12.5 is because the supplier confirmed that the actual thickness of the nominal 12mm thick polycarb plate can vary between 12 and 13 millimeters. So I took the median. But in the instructions for the practicum, I clearly state that this side plate right is manufactured from a 12mm thick polycarbonate plate, and so the thickness will indicate as a reference dimension as 12mm. So here you can see the total length, or the overall length, as 350. I selected a tolerance of plus minus 0.5. I wouldn't go much smaller than plus minus 0.2, and I also wouldn't go much bigger than plus minus 0.5. And the same for the height, 214 plus minus 0.5, not smaller than 0.2, plus minus 0.2, and not much bigger than plus minus 0.5. That's my recommendation. Then the thickness, specifically indicated as a reference dimension, 12 millimeters, not 12,5 as the step file is, but 12 millimeters. This corresponds to my instruction video that I made available on YouTube. It was on the 22nd of March 2023, and the title of the video is mow217 practicum 4 guidelines. So have a look if you are interested to watch that video again. It's mow217 practicum 4 guidelines. So in that video I explained that the way that this side plate right will be manufactured, it will be placed a standard size sheet of 12 millimeter thick polycarbonate plate will be placed on the bed of a 3-axis CNC milling machine or router, and the CNC router will then machine all the features and cut out the side plate right from above. That's important. The reason why I'm saying that is we are now at the stage where we can define our datums. Okay, so immediately from what I've explained relative to how this side plate right will be machined, you can immediately see and say and define datum A as the bottom surface of the side plate right. Everything will be machined from above. Datum A is the bottom of the side plate right. Okay, so on our OCR form in section AA, I've indicated datum A, and you can use the same letters as what you use for the section. The fact that it is in a box, etc., makes it clearly distinguishable that this is a datum. Okay, and then on the front view, we indicate the bottom surface as datum B, and in terms of its orientation, we specify perpendicular to within 50 micron or 0.05 millimeter relative to datum A. And note the leader line is perpendicular to the extension line. You can also connect the leader line to this to the line indicating the surface as well. Datum C is similar. Just a note, datum B is removed from it is separated from the dimension line. That's very important. The same goes for datum A. It's separated. The leader line of the datum box is separated from the dimension line. That's important. Otherwise, we would be referring to the symmetry plane, which is not what we want. We definitely want to specify the bottom surface as datum A. And here the same, we don't want a symmetry plane to be the datum, so there's separation between the datum leader line and the dimension line. The same goes here. There's a separation, clear separation from the datum leader line and the dimension line. What is different from datum B is now we say this datum is perpendicular to 50 microns relative to A and B. Okay, in this case, datum C is not yet defined, so datum B is perpendicular to datum A. That is our secondary datum that we will use for the dimensioning. But in the case of datum C, by this time we have the other two datums, so we can say perpendicular relative to A and B. Okay, so what we will do next is indicate the theoretically exact dimensions of the counterbore holes, as well as the height of this bearing feature on this view, on the front view. Note, ladies and gentlemen, where there is a section view indicated on the front view, the dashed line indicates that all those counterbore holes, the dowel hole and the dowel slot, they are all in line. But in the case where there's not a section line, you have to, with a dash dot line, show that these two holes are at the same vertical position. The same with these holes over here. They are at the same vertical position. So you need to put in that dash dot line. So in order to get the sizes, the dimension, the magnitude of the theoretical exact dimension, let's go to FreeCAD, manipulator workbench, and for this scenario we will use the probe. So we will say from that vertex. Okay, and we need to have a look. The green, it's not that visible, but the green axis is the Y axis. So it's 15 millimeters in the Y direction. And I've indicated the 15 on the front view of this side plate, right? Let us now measure the X distance or the horizontal distance from this vertex to the center of each of these counterbore holes in FreeCAD. So if we do that, we can once again open the manipulator workbench and yeah, let's click that vertex, this line. So we are now looking in the X direction, and that's 31 millimeters. All right, so 31. We'll make a mental note of that, and then between each of these holes, that's 96. Between those two holes, also 96. And between the last three holes, that's also 96. So on the front view, I've now indicated the theoretically exact dimension of 31 and the 396 dimensions I've also indicated. What we will do next is we need to indicate the theoretically exact dimension from this edge to where these three counterbore holes are, as well as the distance from datum C to where these three holes are. We also need to indicate that. So if we go to FreeCAD, we can then measure. The X dimension of this measurement is 15. The Y dimension we already know is also 15, but we are interested in the X dimension. It's indicated with the red axis. So the other dimension that we want is from the edge to these holes. Let's see. Well, for that matter, you could do that as well. So the X dimension for this hole is 335. So let's indicate those two theoretically exact dimensions. So on the front view, I've indicated the 335 basic dimension from datum C to where these three holes are. And I've also indicated on section view AA the distance from datum C to the center of the dowel hole. Now I've deliberately indicated this theoretically exact dimension on this view because this is also where I'm going to dimension the diameter of the dowel hole. So then the theoretically exact dimension and the diameter are on the same view, and also on this view I want to dimension the length between this dowel hole and where the dowel slot is. I'll get back to the dimensioning of the dowel hole and the dowel slot in a few minutes. For now, we are still busy indicating the theoretically exact dimensions of all the counterbore holes, and we've progressed well. The only remaining theoretically exact dimensions are from datum B to these three pairs of counterbore holes. So we want the vertical dimension from down here to here, and from here to here, and from here to here. So let's quickly measure that on FreeCAD. So let us select and select all the dimensions we've already done and delete them. Okay, so what we want is the distance from there to there, and specifically we want the y direction or the y dimension, and that is 45. Okay, let us do it on this side. So from there to there, that is 77, and from there to there is also 77. So you could have indicated the 45, 77, 77 on this view, but what I prefer to do is to indicate it on section view BB, as you can see over here. The reason why I'm doing that is on this section view is the detail or the reference to the detail view of the counterbore holes. So in other words, it's related, these dimensions are related to each other, and that's why I prefer to do it like that. But for now, let's just quickly have a look. So we've got the height of those three holes, we've got the horizontal dimensions, we have the vertical dimension, the horizontal dimension to these three holes, and we also have the horizontal dimension to these three holes over here. That's on this view over here, this 15 millimeter. And then we've got the vertical dimension to the three pairs. So all the, that is what we just spoke about. So we've got those three dimensions. So in other words, all the locations of the relevant respective counterbore holes are all defined. We can now dimension the counterbore hole. So to dimension the counterbore holes, we obviously need a few measurements. So let's quickly do that. We can click on that icon over there to get the radius of an arc or a circle. So this radius is 3,3. So the diameter is 6,6. So if we now look at this table that I've made available on ClickUp, the metric cap screw, the counterbore and clearance drills. So you will see that 6.6 is midway between this 6,4 and 6,8. So if we just go to the left, that's an M6 cap screw, in other words. And if we want the counterbore diameter, it should be 11,2. Okay, the depth of the counterbore is indicated here as 6. So this counterbore depth of 6 millimeter is indeed from the top of the counterbore. Okay, so what it means is if we machine the counterbore hole, we'll come in from that surface and machine it at least 6 millimeters deep. The counterbore diameter of 11,2. The problem is the way that we designed this Shigley-Hauler gearbox is we fasten these polycarbonate plates from this side. And if the counterbore diameter or counterbore drill is not deep enough or is too deep, there will be a problem with the fastener sticking out at the back and pushing against the aluminium profile that you see. If it's not deep enough, it will obviously not engage enough in this T-nut, what is called a T-nut. Okay, I can actually right. So in order to counter that problem, what I suggest we do is dimension the depth of the counterbore from relative to datum A. So we don't dimension the depth of the counterbore. We dimension the depth relative to datum A. Okay, in other words, this dimension. And you will gather that we're going to measure or indicate that dimension on section BB, but we'll get to that in a minute. Let's first measure what this dimension is. That's not what I wanted to do. Let me just quickly delete all these. What I wanted was that. So from there to there, that's 6 millimeter. So on detail 2, I've now indicated the diameter of the clearance hole, and this is the diameter. Okay, let me just say, I've also indicated there are 10 of these holes. They are diameter 6,6 plus minus 0,2, so loose tolerance. And very importantly, it is on the clearance hole that we put the positional tolerance, not on the counter bore hole. We put it on the clearance hole. So there we say positional, diameter 0,3, also quite a loose tolerance relative to primary datum A, secondary B, tertiary C. In the memorandum that I made available, I put datum B as the primary datum, C as the secondary, and A as the tertiary. But in hindsight, I think this is a better strategy to follow. A being the largest surface as the primary, B as secondary, and C as the tertiary datum. So next we'll dimension the dowel hole and the dowel slot. So let's start off by measuring the size of the dowel hole. That's radius 5,025. So it is if we do the calculation 5.025 and we say that equals that cell multiplied by 2, 10,05. Okay, and being a dowel hole, it will make sense for us to once again specify an H7 tolerance for that hole. Okay, so let's type in the 10,05 there. So it's still plus 18 plus 0. So on section view AA, I've indicated the diameter H7. I showed the tolerance range. I also extended the leader line and indicated a better surface texture finish, or the surface texture finish of 1,6 RA. And I've also in line with the dimension line. This is very important because we're talking about the center axis of the hole needs to be positionally constrained to within a diameter of 0,1, which is a reasonably tight tolerance relative to datums A, B, C. And as with the counter bore holes, the clearance holes actually for the counter bore cap screws, I would in hindsight recommend that you use datum A as primary, B as secondary, and C as tertiary. So now we will dimension the dowel slot. It's indicated here in its section view. This dowel slot, that's also detailed in detail view 1. That is what we're going to do next. So what my recommendation is here is that we constrain the, if I can go down to detail, yes, this section view FF. Over here we can constrain the positional placement of the dowel, of the symmetry plane of the dowel slot. We can constrain it in terms of datum B and obviously datum A. But we want to constrain the location of the dowel slot in the vertical direction basically. So if I can repeat what I just said, we're going to define and constrain the symmetry plane of the dowel slot in the vertical direction relative to datum B. That's what we're going to do on this section view FF. In order to do that, let's just take a measurement of the width of the dowel slot. We can go to this icon over there and we can click that point, and there you can see it's 10,05 as with the dowel hole. Okay, and we know, but we can double check that if we click the arc and we click this point over here. What is the Y dimension? Is 15 millimeters, and that we already knew actually. If we look at this front view, that dashed dot line goes through the center of the slot. Okay, so we already knew that distance is 15 millimeters, corresponding to this theoretically exact dimension. We now also know the width of the slot. The last thing that we need to measure is the length of the slot. So let me just select these dimensions in the model tree and delete them. And then we can do, yes, let's do the probe. Yes, it's all the same actually. We can click that arc, click this arc, and it's 4 millimeters long. Okay, we could have also just simply click on that icon and selected this edge. It will be the same value, 4 millimeters. All right, so let's quickly, before we go, the other measurement that I want to take is the location of the dowel relative to dowel slot, rather relative to the dowel hole. So if we do that and we click on this, on that arc there and this arc over here, okay, we get a 318 millimeters. So on section view AA, I've indicated the length at 318, and I've given it quite a loose tolerance, plus minus 0,3. So that's from the center of the dowel hole to the center of the first arc of the slot. Then the length of the slot is also indicated here as 4 plus minus 0,2, also quite a loose tolerance. Now on section view FF, what I've done here is I've first of all I've extended the leader lines, and I've indicated a good surface finish, RA 1,6 for both sides. Okay, because the reason why that is important, if I can just show you on my so the dowel will make contact on the flat surfaces. Okay, the dowel is not going to make contact on the arcs, it's going to make contact on the flat surfaces of the slot. So that's why on our drawing, these surfaces are are important in terms of surface texture. Now I've indicated also here, note no diameter sign, only 10,05 H7 plus 18 0. This is now the height of let me show you on this view. So this is now the slot width that I'm indicating there. The slot width is 10,05. Okay, so let's just go back there. Okay, so 10,05, then in line with the dimension line, I've got the leader line to the tolerance box. So that means I'm specifying the location of the slot in the vertical direction. There's no diameter sign. It's actually the location of the symmetry plane of the slot. That is what I'm constraining here to comma 1 relative to A, B, and C. Okay, I think in the memo I put down 0,05, which I think is unnecessarily tight, so comma 1 should suffice. Okay. Then the other thing, the last thing on detail 1, I just showed 2 times full radius, and that is because the slot will have the slot width has a tolerance. So if you now tolerance the arcs separately, then you might end up with a step here, okay, which is not what we want. What we're saying with 2 times full radius is that the radii need to follow the slot width. That's what we're saying. So now the only remaining detail that we need to dimension is this bearing interface over here. Once again, we won't be dimensioning these 2 bearing interfaces as part of this practicum, but if you were to manufacture this part, you would obviously have to dimension them. But for practice purposes, exercise purposes, we will only consider this detail over here. So the first thing to do is to find the distance from our datum B to the vertical distance to the center axis of this bearing interface, as well as the horizontal distance from datum C to the center axis. Now, in order to do that, we'll go to FreeCAD. We'll delete those dimensions, and then maybe the best would be to do that. Yes. Okay, so we want the distance from that corner to any of these circles. You can select. Okay, and now we must just check the Y direction is the green axis, so Y is 168, X is the red axis, that's 55. So we can now show these 2 theoretically exact dimensions. So on the front view, we've now indicated the horizontal distance, theoretically exact dimension 55, and the vertical theoretical exact dimension of 168. So what we'll do now next is we'll measure the diameter of this bearing interface. In order to do that, let's click this icon, select, that's not what I wanted to do. Let us just delete a few of these dimensions, alright, and try again. So we want that diameter, and the radius is 10,525. So if we go to our spreadsheet, it is 10,525. So the diameter is 21,05, and we know it's a bearing interface. Okay, that's evident from the assembly view. You can see that there's a bearing sitting there in that interface, so it's important that we have a good tolerance there. We'll use an H7 tolerance. So it was 21,05. So if we type in that in our spreadsheet, 21.05, H7 is plus 21 plus 0. Alright, so we've got the size, so we can now in actual fact dimension that bearing interface. So on detail 3, I've now indicated the diameter dimension, diameter 21,05, H7 plus 21 micron 0, and below the diameter dimension, I've indicated the positional tolerance, diameter, 1 relative to A, B, C. As before, for the counterbore holes as well as for the dowel hole and dowel slot, I'm selecting datum A as the primary, B as a secondary, and C as a tertiary. This is, in my mind, or in my view, a better strategy than to say B is the primary, C secondary, and A the tertiary. So what I've also done is I've extended the leader line and indicated the surface texture of 1,6 micron RA. And then what I've also done, in line with the dimension line, I've added a datum box with a leader line that is in line with the dimension line. So in other words, I'm referencing the center axis as datum F, and you will see in a minute why I did that. Note, ladies and gentlemen, the surface texture symbol needs to point in the direction of where there is material. So the material is below the line. This surface texture cannot point upwards. Okay, if it was on the top leader line, then it would point upwards because the material is above the line. So next we will dimension this shoulder. There's a diameter that we need to measure, as well as the shoulder thickness. And as with the counter bore holes, we will dimension this thickness from datum A. Datum A is the surface at the below, or towards the left of this detail view. So we definitely will dimension it. That we will dimension the thickness from datum A upwards. We will not dimension this thickness. So in order to measure, let's quickly go to our, our FreeCAD file, we can select those dimensions, delete them. Alright, with the get radius of arc or circle, we can click on that arc. The radius is 9,3, so let's just quickly type that in our spreadsheet. So it's diameter 18,6, and then so to measure the thickness of that shoulder, let's click on that edge there. It's 2,5. Okay, so over here I've now dimensioned the shoulder, the diameter 18,6. I selected a tolerance of plus minus 0,1. I don't want to go too big here, because as you will see when we discuss bearings, this diameter needs to be the maximum size of that diameter is constrained, but that's something we'll discuss later on. So if you make the tolerance too big, and the manufacturer utilizes the tolerance to the upper end, there's a chance that, or you don't want in any case, this diameter to go too big. The shoulder thickness is also specified relative to datum A, that's important. And then in line with the dimension line, there's a tolerance box constraining the center axis of the shoulder to be concentric, diameter 0,1 relative to datum F, which we've defined over here. There are two more details on the memorandum that I will quickly insert. Before I do, this radius, this fillet radius, needs to be a maximum of 0,3. Now once again, that detail will become clear later on when we discuss bearings. So that's a specification from the bearing manufacturer. That's the one thing. And then the other thing that I want to add here is a cylindricity constraint on the diameter. Okay, so that's really optional, an optional extra. It's strictly speaking not necessary. But that's something that I want to do just to highlight to the manufacturer that the concentricity of this diameter is indeed important. So here you see the maximum radius of that fillet indicated, and also the cylindricity of 0,03. Now this is in the same ballpark as the tolerance, the H7 tolerance for this diameter 21,05. being 21 micron. So here we're talking about 30 micron. So it's in the same ballpark. So next what we will dimension is this chamfer. It's the chamfer. If you on the step file you can clearly see the chamfer. There's actually a drawing mistake on this drawing, in the sense that that 45 angled line is not shown here. So but be that as it may, we can still dimension that chamfer. Now in order to do that, let's just take a quick measurement. Let's select in the model tree and delete those dimensions, and then measure from center to center. So it's 0.6 millimeter, and we will have a tolerance on that value, as well as the angle is obviously 45 degrees. Yes, what one can do is measure the angle, if you want to verify that, between that line and this line. So it's 135, so 45 degree is indeed the chamfer. It's 180 minus 135. Okay, so I've dimensioned the chamfer. The reason for this chamfer will also become evident a bit later on. When we look at the part that interfaces with this detail. Okay, so just hang on a little bit to understand the reason why this chamfer is important. Next, we will dimension the 6 tapped holes, 2 of which are indicated on this detail 3. So there are 2 things that we need to measure here. The first is the distance between these 2 center lines. That is equal to the pitch circle diameter of the 6 holes. Now in order to do that, let's just go to our FreeCAD model. We can once again in the model tree select the dimensions, delete them. Let us do that one and that one. So the distance is 45 millimeters. Okay, and then we also want the diameter, just to confirm. So it's a radius 2,1, diameter 4,2. So in other words, this will be an M5 tapped hole. That was also clearly communicated in the input file or input document and input video for this tutorial or practicum rather. Okay, so I've indicated the 6 tapped holes. They are M5 by 0,8. In my preparation video, I said I think the pitch is 1 millimeter, but the pitch is actually for an M5 coarse thread 0,8. Then equispaced is in a box, so it means that these 6 holes are equally spaced about datum F. Datum F is also, we'll talk about that a bit later on, but the equispaced means if we look at this view over here, there's a 60-degree angle between each of those holes, because it's 360 the revolution, and the revolution is divided in 6 equally spaced segments, each measuring 60 degrees. Okay, so datum C is important because we want the orientation of these 6 holes to be relative to datum C. In other words, the top and bottom holes, if you draw a line through them, that line must be parallel to datum C. So that's why datum C is important. Datum A is our primary datum, as discussed before. And datum F is then our it indicates actually the axis about which this 45-degree pitch circle diameter is centered. Okay, you will notice the .3 is a reasonably loose tolerance, so to prevent the holes from being skew relative to datum A, we can add a perpendicularity tolerance of diameter 0,1 relative to datum A. So with that, we've actually dimensioned all the features related to practicum 4, excluding these 2 bearing interfaces. But as I've said a number of times, those two are basically a repeat of what we did here. So it's unnecessary to worry about that. The last thing that I asked for the practicum are the notes. So let's just quickly have a look there. You need to specify the material as polycarbonate. The Impex is a trade name for mow217 plastics, so it's a polycarbonate plate. I could have added 12mm thick, and I should have done that actually, so that will be more complete, although I did add the reference 12 thickness over here, so but it would have been better to say 12mm thick polycarbonate plate. Surface texture is RA 3,2 unless otherwise specified. So for example, this bearing interface and the dowel slot and hole, those are all 1,6. Break all unspecified sharp edges to 0,3 max by 45 degrees plus minus 5. Unspecified, so in this case we've specified a specific a fillet radius, or a chamfer with a tolerance, and as I said earlier, it will become clear why in the next practicum. Now all unspecified fillet radii to be R 0,4 max, okay, and this one is specified as 0,3. The surface finish, there is no surface finish needed. So these are the standard notes for any detail mechanical drawing. If you have anything more specific related to your mechanical component, then sure, you can add additional notes, but in 85-90% of cases these 5 notes will suffice. So with that, we've finished the detail mechanical drawing of this side plate right, as well as the base profile stage 2. And thank you very much for watching. I do hope that you enjoyed this video, and you are welcome to contact me should you have any uncertainty or questions that you would like to raise. Thank you very much.